Since the proposal of the famous Apriori algorithm, there have been many interesting extensions or improvements towards this method. Let's just examine some of them. Okay. So the first line of work is how to reduce the number of passes of transaction database scans. We know the database scan involves disk accessing, which could be quite expensive. But if you want to find size 10 frequent item sets, likely you have to scan this database 10 times. That's quite expensive. To reduce the number of scans, so there are several publications. One is called partitioning method we're going to introduce. Another one called dynamic item set counting method. You'll probably notice the first author, Serge Brand, who was a PhD student of Stanford University. The second year, 1998, he actually proposed one of the most famous algorithms, PageRank, and set up a Google company. Okay. So another line of the work is how to shrink the number of candidates. You generate a very large number of candidate sets in many cases. How to shrink the number of candidate sets to be generated could be a big saving. Hashing method is an interesting one. For mining max patterns, Bayardo also proposed pruning by support lower bounding. Another interesting method is Bonin proposed sampling method. The third line's work is to explore some special data structures, like some tree projection method using H-tree to do H-minor. And hypercube decomposition is another interesting method. We're going to introduce a new tree structure called FP tree. Let's look at the first one, partitioning method. Partitioning method guarantee you only need to scan data twice, before you generate all the frequent item sets, no matter for how many Ks it is. So they observed a very interesting property called any item set potentially frequent in the transaction database must be frequent in at least one of its partitions. That means, suppose you get a global big database, big transaction database, you partition them into K partitions. If an item set X is not frequent in any one of these K partitions, it cannot be frequent in this global transaction database. Why? You probably can see. If you got an item set X, which is not frequent in the first one, not frequent in the second one, not frequent in the case one. So you add them together. You add all these support together, you get a global support. You add all these database together, you get a global database. You probably can see if everyone is smaller than sigma times its size, then finally the global one were also smaller than sigma times the size of global database. That's why at least one of these database contain must be frequent. Okay. So with this observation, okay, you can see this partitioning method will need only two scans. The first scan is you partition the database into K partition database. How do you partition them? Each partition you want them to fit into the main memory. Why? Because no matter how you scan them, you will not involve any database IOs. So that's the reason you can scan once you put them in the database, you can work on it to derive K frequent item sets for no matter how many Ks you can get. Okay, that means you can derive all the local frequent item sets. Okay, then based on this property, you can do the second scan like this. Okay, you can say, since any frequent item set in one of these K transactions can be potentially frequent, so the globally candidate sets which is frequent in any one of them, it will be a global candidate item set. Then the second scan, you just count against each database, count those counts of the global candidate sets. Okay, then you will get their count, you add them together, you will be able to derive global frequent patterns. That's why this method guaranteed to scan database only twice. So this is pretty interesting. Another method I'm going to introduce you called directly hashing and pruning. This method is trying to reduce the number of candidate sets based on hashing and pruning techniques. The general philosophy can be like this. Okay? The observation is, if the k item set is frequent, then in this hashing bucket, it contains several potential item sets. It must be frequent. So if the hash count is not frequent, then any one of them cannot be frequent. The general philosophy like this. Okay? While you are going to derive the frequent one item set, in the meantime, you set up a hash entry for the potential two item sets, but why you set a hash entry rather than count each one? Because there could be many, many distinct items. So the frequent two item sets before you get a frequent one, the candidate two could be really, really big. But if you set a hash entry to get several items share one hash entry, the whole hash table will not be too big. Okay. Then the interesting thing is, while you derive frequent one item set, you also can cut many two item sets. They cannot be frequent. For example, suppose our minimum support count is 70. Then this one has only 35. This one has only 58. That implies those items, none of those items can be frequent because they share this entry. Their support count is still below the threshold. So only the second one, this BD, the support is quite big. Past the support threshold, this may contain the real candidate sets. Okay? That's the reason you can reduce the number of candidates substantially using this hashing and pruning method.